In the previous videos, we looked at how to calculate the eigenvectors and eigenvalues of a matrix. In this video, we'll show you one example how we can use eigenvectors and eigenvalues to solve an engineering problem. Before going to the details of the example, let's look at what happens when you multiply a function by a matrix. Assume we have the function fx, and we multiply that by a matrix A. It will perform linear transformation on the function by matrix A. What does it mean by linear transformation? If the function fx describes a square, the linear transformation can do three things. It can stretch the shape, it can shear the shape, it can rotate the shape. However, it cannot bend the shape. You cannot get this shape from linear transformation. Then, what is the physical meaning of eigenvalues and eigenvectors? Let's look at the shear example. Before shearing, we have a square, and these are the coordinates for the four corners. Now we apply the shear, and this is the new shape. During the linear transformation, you will notice this vector remains the same as this vector. It's not a perfect square, so it looks a bit weird. It should be along the same line. So the two arrows we draw here is one of the eigenvectors in this matrix. The points on the eigenvector will not rotate during the linear transformation, and how much it has stretched along the same direction is called the eigenvalue. So the eigenvalue in this case specifically is 1. By the way, the vector here is not an eigenvector. This is because after the linear transformation, it has rotated to a new position. Now we're ready to look at the example. In the example, we have an elastic membrane, and at the center of the elastic membrane, we draw a circle. Now we apply a force to stretch it, and after stretching, the circle develops into a new shape. The matrix corresponds to this stretch, can be written down as this. The question asks for the principal directions where the membrane is getting stretched. Based on what we just described, we know this question really asks for the eigenvectors of the matrix. Mathematically, it's very simple. What we need to do is to construct a new matrix using the entries along the diagonal minus the eigenvalue. Then compute the determinant and set the determinant equal to 0. We can easily get and solve lambda. There are two solutions. For lambda 1, it is equal to 8. For lambda 2, it is equal to 2. With the eigenvalues, we can calculate the eigenvectors. For lambda is equal to 8, we can create a new matrix. Writing that into linear equation form, we have x1 equals to x2. So any vectors along this line is an eigenvector. How about lambda is equal to 2? Again, we'll construct the new linear equations. And we will have this relationship. x1 is equal to minus x2. If we plot it, we'll get something like this. So any vectors along the second line are also eigenvectors for this matrix. What's the physical meaning of lambda 1 and lambda 2? 8 and 2. That means along one direction the stretch is 2 or twice, and along the other direction the stretch is 8 times, to linearly transform the circle into an ellipse. You can tell from this example doing matrix multiplication and understanding the eigenvectors and eigenvalues is immensely important in image processing when you try to manipulate shapes. From the next video, we'll move away from the eigenvector and eigenvalues and enter a new topic. We'll start discussing the vector differential calculus.